I first want to remind you that the Fourier series, there's really two forms that are identical, the complex form and the real form. The form people most speak of naturally is actually the trigonometric form of the synthesis equation, which says that a periodic function can be decomposed as a sum of cosines and sines. And one of the most natural questions you can ask about a Fourier series is just asking, how can I take a Fourier series of some function like f of x equals e to the x? Which might seem contradictory because, well, f of x isn't periodic anywhere, so its Fourier series doesn't really make sense because Fourier series is intended for periodic functions. When we speak of Fourier series, what we really care about is some predefined interval of interest. So let's say we want to take f of x equals e to the x on negative pi to pi. We're going to take this Fourier series there by making a periodic extension of that. To show you what that means, here I take f of x equals e to the x on the interval negative pi to pi, and I'm going to form its periodic extension over the whole line, or here I want to show you from negative 5 pi to 5 pi, and it's going to repeat every 2 pi because that's its period. When I take its Fourier series by the analysis equation and the Fourier series together, the Fourier synthesis equation, what you'll get is this following here. And I'm going to show you in this top row, you're going to see the Fourier synthesis over 5 terms, 10 terms, and 50 terms. In the second row, I'm going to show the error, and the points I want to get across from here is 1, increasing the number of terms generally improves the approximation. And 2, the error is highest near the endpoints. You can see that here on the squared error. The reason for why the error dies out is because you inherently try to form an approximation when the function was discontinuous at the periodic extension. You can see in the original graph of the extension, it's going to be discontinuous because the function itself wasn't really actually periodic at that point. And the last point that I want to mention has to do with the magnitude of Fourier coefficients, and that says really that for the Fourier series to converge, eventually their coefficients are actually going to decay. So here I plot the cosine terms, the cosine coefficients, and over time the harmonics at the later end are actually going to go closer to 0, eventually to 0, and that's what's needed for convergence. And also it's what really makes sense that later on the higher frequency terms contribute less and less and less for the expansion.